I'm going to look at all the examples on stationary points again, but using an alternative method to the sine table called the second derivative. So we have y is equal to x cubed plus x squared minus 5x minus 4. Differentiating once gives us the first derivative, dy dx, and that's going to be 3x squared plus 2x minus 5. Now to locate stationary points, we want dy dx to be 0, so 3x squared plus 2x minus 5 is equal to 0. So we can factorize that. We want 3x and x, and we'll need the 5 in this one and a 1 in this one. And if we do plus and minus, that gives us that x is negative 5/3, or x is 1. Now I'm not going to worry about the coordinates here. We could substitute both of those back in to find the corresponding y. So instead of using a sine table, we're going to use the second derivative. And that means that we differentiate this one again. Now when we differentiate dy dx again with respect to x, we get what's known as d2y dx squared. And that's going to be 6x plus 2. So if we do d2y dx squared and we evaluate it when x is negative 5/3, we get 6 lots of negative 5/3 plus 2. So that's negative 10 add 2, which is negative 8. And d2y dx squared evaluated when x is equal to 1 is equal to 8. Now the important thing is that this one is negative and that this one is positive. The rule with the second differential says that when it's negative, we get a maximum. When it's positive, we get a minimum. So that tells us that this one here is a local maximum and that this one here is a local minimum. So remember, with the second differential, d2y dx squared, if it's negative, that means that we have a maximum. If it's positive, that tells us we have a minimum. Now a lot of students therefore think that if it's 0, that means a horizontal point of inflection, but in fact 0 tells us nothing. At least 0 tells us nothing when dy dx is 0 as well. So if it's 0, it could actually be a maximum, a minimum, or a point of inflection. So in this particular case, we would then go ahead and use a sine table.